Hi everyone, in this video I'm going to talk about how speed of reactions for steps can help you determine the rate laws of the reaction. So as a refresher, a lot of times reactions happen in multiple steps, even if we don't show that. When I say this is the chemical reaction, if a step only has one reactant, it's known as unimolecular, and it would look like this: A becomes product. If it's a bimolecular step, it has two reactants, and it could look like this: A plus B makes product, or A plus A. Sometimes A plus A won't be written like that. Actually, I would say all the time it would be written like 2A makes a product. That's a bimolecular step. You have two reactants. Termoleculars have three reactants. And so really fast, especially the examples at the bottom, how that would be written would be like 3A. How this would probably be written would be 2A plus B. Both of those are termolecular reactants because I need three molecules to collide and hit at the same time. And you can write rate laws for steps based on stoichiometry, which I have the examples here. So sometimes we're given information about the speed of the steps in a reaction mechanism. Like you're told this step is slow, this step is fast. Your slowest step is known as the rate determining step because this one determines how fast the reaction can go. That should say rate determining step. I can't talk and write. So for example, if you were in a chocolate factory, it takes you 15 minutes to make chocolate, 8 hours for the chocolate to cool, 5 minutes to box it. You could probably speed up making the chocolate. You can speed up boxing the chocolate. You can't really speed up the chocolate cooling because that's how long it's going to take. And so our rate determining step would be the cooling, because that is the slowest part of this reaction and determines how fast you can make. And I can, as it says, you can speed up everything, but until the cooling speeds, the reaction speed is not going to really change. So your rate determining step is your slowest step, and it determines the entire reaction's rate because it slows it down. And so if the first step of a reaction mechanism is the slow step, then the overall rate law is based on the stoichiometry of the first step. Again, if the first step of the reaction is slow, the overall rate law is based on the stoichiometry of the first step. What does that mean? Let's look at this example. Step 1, step 2, example, step 1 is slow, step 2 is fast. So step 1 is our rate determining step. And because it's the slow step, the overall rate law for this reaction is based on the stoichiometry of that step. So I would say the rate law for this reaction is, well, first actually let's write the reaction. So if I combine those two steps, what is the overall reaction? Well, let's look. B is made and then it's produced. That's known as an intermediate. So my reaction would be, I could say A plus A. Usually we would say 2A plus C makes D. That is the chemical reaction. That would be like what you do your calculations based off of. But for the rate, again, because step 1 is my slow, it's my rate determining step, the rate law for this reaction is based on step 1. And what is step 1? Rate equals, K, because every reaction has a rate constant, times A, and there are two of them, so I square it. Again, this is the rate law for that reaction, and it's based off of your slow step. C is only dealt with in a fast step, so it's not really influencing the reaction rate. That's why we don't include it. It goes really fast. It's the slow step that determines the reaction rate. Let's look at a few more examples. And the reaction to CHAP makes CH2 plus AP2 occurs in a single step. Write the rate law for this reaction. Well, if it occurs in a single step, that means this is step 1, it's the slow step, it's also the fast step. So because it's the slow step, the rate law is, what's the stoichiometry of that step? Rate equals K chap squared. I square it because there are two of them. 2. Write the rate law for a reaction that takes place for this elementary reaction. Sometimes if you see elementary reaction, that is another way of saying for this elementary step. So what's the rate law for this step? Rate equals K O3 times NO. And a few more. This 3 has a bunch of steps. Let's look at it. So scientists have suggested 2 different mechanisms for the same reaction. The steps for each suggestion are listed below. So I've got proposal 1, proposal 2. A, what's the overall balanced equation for this reaction? So to figure that out, I need to look at each proposal. They shouldn't add up to equal the same, but let's be careful. So C is made and then it's used. It's an intermediate. It's not going to be included in the reaction. And then I start with 2 A's and there's an A in the product. So that's going to cancel with one of those. And so we're left with the reaction as A plus D makes B. This should add up to equal that, but let's just check. So A squared, those cancel. E is a reactant, then a product, so it cancels. And an A is going to cancel with an A again. So we are left with A plus D makes B. So yeah, that would be my overall equation. A plus D makes B. B, what's an intermediate in the reaction? Again, an intermediate is a product, then a reactant. So in proposal 1, the intermediate is C. It was made and then it was used. In proposal 2, the intermediate is A squared. It was made and then it was used. E was used and then it was made. That is not a reactant. We'll talk about that later. Or sorry, that's not an intermediate. An intermediate is made, then used in that order. So C, what's the predicted rate law for proposal 1? Step 1. So rate equals, and again, if you're asked for the rate law for a step, it's just based on that step's stoichiometry. So K A squared. I square it because there are 2 A's. What's the predicted rate law for proposal 1? Elementary step 2. Rate equals, step 2 is C and D. So K times C times D. What's the predicted rate law for proposal 2? Step 1. Looking at this, rate equals, again, it's just a stoichiometry. So K A squared times E. I'm squaring A because there are 2 of them. For proposal 2, step 2 would be rate equals K A2 D. So G, if the observed rate law for this reaction was this. So this is the rate law for the whole reaction. Which proposal is correct and which one is the slow step? If that's the rate law for the whole reaction, that matches this. So proposal 1 is correct. And the slow step is step 1. I know step 1 is slow because if this is the rate law for the whole reaction and it matches step 1, that means step 1 must be slow. Because again, when the slow step is first, the overall reaction's rate law is the stoichiometry of the first step. Again, when the slow step is first, the overall rate law is the stoichiometry of the slow step, if the slow step is first. And then last questions. Scientists have suggested 2 reaction mechanisms for this reaction. So this is the overall reaction. Proposal A says this happens in 1 step, 2ICl plus H2. Proposal B says it happens in 2 steps. Why is choice B a more likely reaction mechanism, and explain? Choice B is going to be more likely to be correct because both of these steps are bimolecular. They only have 2 reactants. Proposal A is a termolecular step, and those are extremely rare. Why? Again, because you need 3 molecules to collide with the right amount of energy in the right orientation. That's just not going to happen. So choice B is more likely because the slow step is, actually both steps are bimolecular. Proposal A is a termolecular reaction, and those are very rare. So write the predicted rate law for this reaction. Again, this is probably the reaction mechanism, not the termolecular one, and my slow step is first. So the rate law is the stoichiometry of the slow step. Rate equals K ICl times H2. So I hope this video is helpful in helping you figure out how to write a rate law for a reaction from steps. My next video, the steady state approximation, will go over how do you write the rate law when the fast step is first and the slow is second, because that's a little bit different.